started the recording.
All right. Please go ahead.
Okay, can you see my screen now?
Yep.
Okay, perfect. And yeah, sorry about the delay. And actually, let me close captioning. So yeah, I'll quickly introduce myself in interest of time. My name is Farhad Ameri. I am an associate professor in the School of Manufacturing Systems and Network at ASU. It's one of the new schools under Fulton Schools of Engineering, which is focused on manufacturing. So my background is also in manufacturing and industrial engineering, but I use like ontology, semantic models, neurosymbolic AI to manufacturing and supply chain applications. So I understand this group is not related to manufacturing, so I apologize if I refer to manufacturing terms and concepts. So my talk has basically 3 parts because I learned that this group already works with ontologies. I'll not go into much details, just a quick introduction to ontologies, make sure we are all on the same page, and then move on to Industrial Ontologies Foundry. It's an initiative with the participation of government, industry, and academia, and the goal is to facilitate use of ontologies in industry. And then I will provide a quick example on agri-food traceability use case where we have used ontologies to support food traceability. So first part, well, why ontologies? Obviously, in manufacturing and service industry, basically, we have witnessed rapid digitalization, and systems are very much interconnected and distributed. Obviously, we have a lot of software systems that need to work together. And in this context, interoperability becomes a problem, an issue. And basically, semantic models and ontologies, their first utility is to enhance interoperability. We have a lot of software systems need to communicate with each other, with data size. Heterogeneity is a problem. We have large number of data silos, data lakes, and data swamps. And well, in this situation, distributed decision-making by distributed agents is actually becoming very, very pervasive in industries. So that's why, again, communication at a semantic level becomes very critical, and we should add meaning to data, right? And ontologies are here to help us add meaning to data such that dispersed agents can communicate and interact. Well, that's a partial solution. Ontologies are not supposed to solve all problems, but that they are part of the solution. So they provide common terminological framework, controlled vocabulary with machine interpretable semantics, and standardized model for describing types of entities and a relationship between them. So in that sense, they can use for semantic unification and harmonization of data. So you have seen this spectrum of semantic knowledge models with respect to development cost and expressivity. Obviously, we have different types of semantic models, like a list, a hierarchy, a thesaurus, a taxonomy. These are all semantic models, but they have different levels of expressivity. So we are at the far end of this spectrum. So we are on ontologies, which are highly expressive, but the problem is that their development cost and effort sometimes is prohibitive. So that's why we need to have real well-defined methodologies for developing ontologies that are reusable. We don't want to start from scratch all the time, right? So, well, in terms of definition, that's the most commonly used definition by Studer, a formal explicit specification of a shared conceptualization. Formality refers to machine readability. Being explicit, it means that concepts, properties, and relationships are defined explicitly. There's a consensual knowledge based on for ontologies, and well, the conceptualization refers to providing an abstract model of some domain. There is another definition by ISO 21838, which is collection of terms, relationship, expression, and associated natural language definitions together with one or more formal theories designed to capture the intended interpretation of these definitions. And here the key entity is actually the formal theories or logic-based formalism. We really need logic-based formalism to support ontologies, and FOL, common logic, descriptional logic are examples of logic-based formalism that are used for ontology support. But well, I guess we are here, at least with this group, we are all on the same page that ontology is not data, but ontology enriches and enhances data semantically, because sometimes people conflate data and ontology. But it's good to make sure that they are not the same. There are two different entities. So different types of ontologies, top-level ontologies like BFO, Dolce, UFO, they are more abstract, philosophical, and generic ontologies. Then when we get to domain ontologies, we become more domain-specific. Like, for example, we have a supply chain reference ontology, which is still generic, but it's focused on domain of supply chain. And then when we get to application ontology, it's more limited in terms of scope. It's designed and optimized for a specific application or use case in mind. And the standard W3C standards for ontologies include OWL, RDF, RDFS, SWRL for rule modeling, and Shackle for constraint checking and things like that. So we obviously would like to use ontologies and their standard languages that support ontologies, because that's one way we can promote reusability. And how ontologies can help, I'm sure you're all familiar. Well, interoperability is the main utility, but semantic search, data integrity, semantic integration and mediation, and the reasoning and inference, they're all critical aspects, and these are different ways ontologies can help. So that's why we use ontologies. Depending on the use case, we'll use one of those utilities. But I would say providing common understanding, that is the global high-level usefulness that in most cases really matters to us. But, well, despite all these wonderful aspects of ontologies, so far, in many cases, they have failed, at least in manufacturing industry that I've worked with closely. Well, it's not being used actively in the US. I mean, Europe, the situation is much better. I know oil and gas industry in Norway, they use ontology on a daily basis. But for US companies, that's a strange term. I mean, that doesn't mean much, doesn't ring any bell for them. But the problems are we have too many ontologies. Everybody wants one. They are built on ad hoc ways. They don't really follow a principled approach. There's no rigorous methodology for developing and annotating ontologies in sufficient long-term organizational commitment or short half-life. If you have a PhD student, works on ontology, develops it, and once the PhD student graduates, then there is no actually after-sales service for the ontology or any support for the ontology. So the ontology dies. Poor communication and support and poor trainings. These are the main reasons that ontologies kind of, at least in our domain, they have failed. In biomedical industry, they are doing much better than manufacturing. So, and for that reason, actually, IOF started to address those problems. It was in 2016 that we started IOF, and again, the goal is to promote use of open source ontologies in industry. It's an international standards group that operates under the auspices of Open Application Group, OAGI, and is kind of modeled after Open Biological and Biomedical Ontology Foundry, OBO. So I'm sure you're familiar with that, but it was a very successful initiative in biomedical industry, and we would like to kind of follow that success and see if we can mimic the same pattern and achieve the same milestones in manufacturing industry. So again, the mission is to create a suite of public and reusable reference ontologies and promote use of ontologies in industrial applications, and it's basically a group composed of government entities, industry, academic institution and standard organization. For example, NIST is a core part of IOF and basically provides a lot of support for us. So current members, NIST, Airbus, Lockheed Martin, several academic institutions. And the good thing is that we work with Europe as well. So the counterpart of IOF in Europe is a project called Onto Commons. They have kind of similar mission. They are much ahead of us in terms of like applications of ontologies because industry really works with them. But here we are just trying to convince industry that, hey, you need semantic models to improve the quality of your data processing applications and business intelligence. So we have about 50 plus organizations, and this list is growing. So we released the first product in January 2023 this year, which is IOF Core. Then supply chain was the second domain level ontology that was actually released in January as well, and the next one will be maintenance ontology. And all these ontologies are available on the GitHub link that you can see, and I'll share these slides with Asiya, so you can always check the links. But all those ontologies are freely available and are open source, and that's the intent of IOF to share them. So a quick organizational structure: we have governance board, technical oversight board, and a bunch of working groups like supply chain, maintenance, systems engineering, material science, production planning. So each working group is supposed to generate one or more domain ontologies based on the principles that are defined by IOF. And here you can see the architecture. So we use a top-level ontology, and the top-level ontology for us is BFO, Basic Formal Ontology, and it means that all classes and properties should have a BFO superclass or parent class. So, and the main semantics are coming from BFO, and it gives us a framework for ontology development. And IOF has a hub and a spoke architecture, so everything stems out from BFO. And well, BFO is again very much philosophical, generic, abstract ontology. You can see these are the entire classes that BFO has. It divides the word into two sections: continuance and occurrence. For example, continuance can be either independent continuance or generically dependent continuance, which is basically all the information goes under GDC, or a specifically dependent continuance like quality, role, function, disposition. So, but here on the occurrence side, these are all the processes like process boundary, or temporal region, or temporal instance. So they are very well axiomatized, but they are very generic, right? So that's why we need to extend and create lower level classes here. This kind of the BFO universe. So we have IOF universe. We have this orbit. We have basically these more mid-level ontologies like IOF core or common core ontology. Again, they are mid-level in a sense that they're very generic still. They can be applied to different domains. But when we go to the last orbit, these are actually more domain level ontologies that are focused on specific applications. But this import structure always exists. So IOF core imports BFO, and then here SCRO stands for supply chain reference ontology, imports IOF core, and then basically any other ontology can import like one of the domain level ontologies. So this import structure is always maintained. We do not need to start from scratch, but we need to reuse existing ontologies to the extent possible. These are some examples of the classes. For example, here you see the occurrence side of the core ontology. So we have different types of business processes like buying, service, procuring, supplying. So all these processes are defined very accurately. I'll show you some examples of axioms as I move forward. This is the material entity side. For example, a factory is a type of facility which is an engineering system, which is actually a BFO object aggregate. So you can see that there's always a connection between any entity and a BFO term or class. then all the information entities fall under generically dependent, continuant, and yeah, so I can send you the link to maybe some information about BFO such that you can learn more about BFO terms and classes, but like algorithm specifications, plans, identifiers, all those informational entities fall under like GDC. So these are some examples of all those information entities. Well, in terms of tools, obviously, still Protege, to my surprise, is the primary tool for developing ontologies, and we still use Protege. So there is RDF XML serialization. We need to reserialize sometimes the output of Protege because the way it represents the RDF XML structure is not sometimes very easy to discern and comprehend. So that's why we internally do some reserialization. Well, obviously, we just don't not only care about the concepts and classes, but the relationship between them matters very much. So this is an example where we have a concept diagram that we specify how those entities are related to each other. So, for example, here are showing a leaking process. Which is basically about solenoid valve. So in that way, we can really accurately describe the scenario, situation, maintenance issue, and then later on, if we want to search for similar scenarios, we can always do a very high level, very semantic and rich search. Well, so we keep saying formal ontologies, but the reality is that a human being also needs to use ontologies. So, right, so that's why ontologies need to be useful for machine and for human. That's why defining natural language definitions or providing natural language definition is very critical. So for each term or class, there should be a natural language definition that complies like with some standards for natural language. I guess we use ISO 704 for natural language definitions, such that it promotes reusability. People can understand what we mean, right? So, and also first order logic. So that part is for machines because that's the logic, that's the maths behind ontologies. So we use FOL as the main logic-based formalism, and each term needs to be defined logically using FOL. And so those definitions are provided as annotation. So, for example, here we have for algorithm as a class. So what's the natural language definition? What's the axiom in first order logic? If there are examples, we should provide examples. And sometimes we need some explanatory notes such that everybody really understands the intent, the intended meaning of the term. And all the context is maintained in that way. Otherwise, algorithm means different things to different people, right? So our goal is to unify those varying viewpoints. So here is again a class annotation for factory. You can see the first order logic axiom and semi-formal natural language axiom, and also natural language definitions and examples. In that way, we have clearly conveyed the meaning, and it's encoded in the ontology. Well, unfortunately, all ontologies, they don't have expressivity of full FOL. They use a subset of first order logic. So they use a description logic, but still we can use all axioms, which are following description logic to define necessary condition or necessary sufficient condition. Yeah, so, but it is, although we cannot be at the FOL level of specificity, we can still say some useful facts about all those terms, and they need to be, and that's the real value of ontologies. If you are not formalizing the terms, then we have just a dictionary. Yeah, I mean sometimes just a dictionary or glossary is useful, but the question is, will it enable automation and machine level interoperability? And that's what ontologies are about. Well, there's always a trade-off. So we get a lot of expressivity, but from the other hand, the complexity of our, if we want to represent data using an ontology becomes more something as simple as this table weighs 80 pounds. If you are using a relational database, it's just one tuple, one line. Table weight 80 pounds. But in an ontology, well, you should really go into detail. So what is weight? So it's a type of quality, and it's a quality of table, and it has been measured at some point, which actually has a value expression, and value expression has the amount or the numeric value and the unit, what's pound itself, right? So, and here we are using QUDT. QUDT is a very highly reused ontology for units of measure. So instead of we creating our own unit of measure ontology, the decision was that, yeah, let's use QUDT. And that's what we are doing. But yeah, you can see that it's not necessarily the most efficient database, but to get expressivity, we need to take that extra step and really delineate all the details very clearly. So I guess I'll go all the way towards the end, right? For Q&A, is that okay if I go all the way to the end and wait for QA?
We still have half an hour. Please.
Okay.
Yeah,
all right.
Go ahead.
For another 15 minutes, and then we can open it for Q&A. I don't want to bore you with a lot of slides. Well, one of the very first steps in ontology development is requirement planning, right? So it's like designing a product or designing a software, right? So what's the purpose, how it helps, what type of problem we are dealing with, and who are the stakeholders, and is it like a reference ontology at a domain level or more application? Do we need a top level ontology, TLO? Or not, or do we have use cases for the ontology, and what are the key terms and notions in that domain, and if their definitions are available. Then once we have those definitions, so this is the process we try to follow in IOF. These documents, hopefully they will be released and will make it available to public, because that's one of the services of IOF. But as you can see, once the use cases have been defined, we need to define competency questions and natural language definitions and FOL, semi-formal and OWL axiom, and then it should be tested. So testing is done through sending queries and running hygiene tests to make sure ontology has the quality we need. And then there is an approval and voting and release process that we follow, such that the ontology is reviewed by multiple people and they look at it from different angles. There are some automated tests and there are some human-centered tests, but as a result, we'll have a high quality ontology towards the end. This is one of the documents that we use to start the process, the use case. Because we really don't want to develop ontology in the vacuum. We need to have a context, a use case. So, and then that's why whoever who wants to start the development process needs to provide a problem statement. What's the pain point here? What type of technical challenge do we have? I mean, sometimes really ontology is overkill. You just need to query simple tables. Why do you need ontologies, right? So, but if there is information sharing and reasoning needs are there, so yeah, then it warrants using ontology. And then competency questions. So these are the type of queries you want to send to the ontology. So, and you hope the ontology can return the answer. So these competency questions are useful and is very much encouraged in the community to define them. It has two purposes. One, you can identify those notions that you care about, for example, aerospace or capability or capacity. So these are the terms that maybe need to be formalized future. And then these are the queries that eventually we need to create them in a SPARQL and send it to the ontology. And that's part of the test. Can ontology return the answers that we need? So that was just a quick overview of the procedure that we follow in IOF. And a few slides about ontologies and knowledge graphs. So there's a lot of confusion. Sometimes people use those interchangeably, and still there is always a a fuzzy or kind of a gray line between these two. But really, I would like to say that, well, for me, the way to separate knowledge graph from ontology is that knowledge graph really is the data side of it. So is basically a connection of real world entities, objects, events, people, and relationship between them. And it contains data. For example, when we say Eiffel Tower is located in Paris, so Paris is a type of city, right? So it's part of data. It's not part of the ontology. It's an instance of city, or Eiffel Tower is an instance of an object or an entity or artifact. So, and this triple structure, subject, predicate, object, is the basic building block of the knowledge graph. But again, the main difference to me is that knowledge graph contains data. And when it's aligned with ontology, then it combines characteristics of several data management paradigms that can be understood as database. So knowledge graph is a database because it contains data. It's a graph because it can be analyzed as any other network data structure. And it is knowledge base because the data in it bears formal semantics, which can be used to interpret data and infer new facts. So we can have knowledge graphs not aligned with ontologies, and that's okay, people do that. But the real value of knowledge graphs comes when they are aligned with ontologies. So in this terminology that's used in ontology domain, like A box and T box. So ontology is more the terminology box outside of the knowledge base, but the knowledge graph itself is the assertion side of the data. And there should be a mapping between those two. And that's where we can actually do reasoning on the knowledge graph. Because of the mapping, we know the meaning, and the meanings are precisely defined within the ontology. There are some commercial tools for knowledge graph generation, RDFX, Stardog, Ontotext, GraphDBs, or Neo4j or Anzo. They are being used and they are being developed or extended very quickly. And the pace of technology development, I realize, is very fast. Within last 6 months, I realized there are 4 or 5 new tools being added to this list. But yeah, it's gaining traction, and maybe large language models and neural network is kind of helping knowledge graph community to accelerate in their development, because there is a lot of interaction between these two, and connection. One can support the other, so that's why the development speed has gone up significantly. So by now, okay, we are on the same page on ontologies, knowledge graph, how ontologies can help, and basic steps that we use for developing ontologies. You've got an idea of what IOF is and what are the objectives. I'll move quickly to one example ontology, agri-food supply chain traceability. This project is sponsored by NIST, and we wanted to see if we can use ontologies to support traceability in food. And so as you are familiar, it first ability to trace and track food products through specified stages of production, processing, and distribution. And it has becoming an increasing concern among government, producer, and consumers. We would like to see what are the sources of the food that we use. And so that's very critical. But it's a challenging problem. There are a lot of participants in this supply chain. The end-to-end traceability requires consistent information, but we have a lot of data problems. We have varying syntax and semantics, inconsistent naming and identification conventions, and incomplete and low quality data. So we focus on grain production, and so there are different steps, from seeding to planting to harvesting, from moving the seeds from combine to cart, and from cart to bins, and bins to trucks, and scaling, going all the way to food processing facility, inspection, unloading, transformation. So there are a lot of parties involved, and their level of technological sophistication really varies. Some farmers they don't have any technology, but some equipment like combines, they have GPS and they have sensors, and they submit data every second. So, but the data is not being used. So we are in such a heterogeneous environment, and that's a sweet spot for use of ontologies. And these are some queries that we want to answer. So in which bin was grain stored for outbound shipment with this given ID, or what type of transformation process took place in the Asheville malting facility, or we can read the rest. But so to reconstruct the history, so that coming from different sources, this is actually a challenging problem. So we used CTD Framework from Institute of Food Technologies. So critical tracking events like transport, load, unload, these are some events that we care about, and they can actually encapsulate the history of the product or the supply chain. So we'd like to identify those CTEs, and there are some key data elements associated to the CTEs. So like date, time, so forth. But if we can really create a CTE view of the grain production process, then the problem is solved. We can actually see all those events and how the material goes through those events. But unfortunately, it's very challenging if our data has full of gaps and it's low quality and it basically is not collected properly. So if we can actually use ontology for semantic harmonization of data from situation 1 to situation 2, when data is actually harmonized and the gaps are filled and they are all using the same semantics, then building this history and tracing and tracking back and forward would be much easier. So we created an ontology called it Supply Chain Traceability. It uses IOF core as basically the mid-level ontology and also supply chain reference ontology, and adopts IOF architecture and principle. These are some class diagrams like transfer events, the temporal aspects of event, how it's captured, beginning of the event and end of the event. Or what's a load? Load itself is a role thing. Everything can be a load. So load is an object or object aggregate that bears a load role. And what's the load role? This is a definition. And these definitions are also represented such that machine also understand what's going on here. For container, like my tabletop can be a container. So that's why container for us is also a role thing. Like, so it's an object or fiat object part that has role, container role, and it can have locations, interior, and so forth. Or things like measurement, what's the moisture content of this grain and how to represent the measurement result. Like, so that's the result. But again, you need to go through all these complex graphs to very precisely describe what that moisture value is. Or here is like the location. You have a grain elevator, so, and its location is identified through a GLN number. So what's a GLN number and what it designates and what type of entity it is. So again, I'll share these slides and you can look at the details. So we tested the ontology using simulation. We created different data in different formats. We focused on CSV and JSON format. So in the use case, we had 600 transfer or transport event, 400 loads, 4 combines, 5 cars, 3 trucks, 2 on-farm storage bins. And well, when we converted the data from CSV file to actually the knowledge graph, we ended up with 290,000 triples. So obviously, we can send SPARQL queries, but well, for domain experts, working with queries is not an easy thing. Even for our own ontology experts, sometimes SPARQL queries poses some challenges. So here you can see some of the queries, like this query is about who were the custodians involved in these custody change events. So that's the query, and you can see the results at the bottom. So who have been the custodian for this TRU stands for Traceable Resource Unit, which is a load. So who has been in custody of this load? So you can see the result in form of a table, also in form of a graph. Here, the visualization tool we use is RDFox. So another example, when was this truck load in custody of this driver, right? So, but again, so that formulating queries sometimes works, sometimes doesn't. So we decided to see if we can streamline the trace and track process through supply chain data visualization. So, and the goal was to try to visualize data. And in that way, maybe it's easier to find those critical tracking events and trace back and forth. So we created a tool for converting those files, CSV files, into graph and alignment. This is an open source tool. I can share it with the group. And basically, there is an alignment with ontology in the backend. Users don't see this alignment. Users just match the columns of the CSV file with these properties that we care about. And so here is the view of the data, right? So instead of having a knowledge graph, which is very huge, or working with CSV files, you're able to extract those events and can visualize the chain of events. And then the domain experts, they can look at this model and see, okay, yeah, so from this field, what type of events have been cared and how the load is going through different stages until they go on farm storage. So we are expanding the tool now such that the widths of these lines kind of shows the amount of material, like 593 BU stands for bushel. So that's an ongoing project, and I can also share papers about this project if the group is interested. But I guess that is my last slide. Yeah, so closing remarks. Well, ontologies are not silver bullets, but parts of the solution. We should not expect ontologies to do everything for us. We need to reuse high quality ontologies to the extent possible. We just don't, otherwise we are contributing to the problem of lack of interoperability and problem of data silos. Instead of data silos, we have ontology silos. It's more than just a taxonomy of terms. It needs to have formal definitions. And KGs are more than only graph databases. If you want to really use the KGs and help us in decision support, they should be aligned with ontologies. And Gen AI needs ontologies for transparency and explainability. So this, a colleague of mine used this analogy that left side of the brain is is the logical side, the right side of the brain is creative side. Yeah, so same applies. So formal ontologies are the logical side, but deep learning is more the creative side. So, but we need both half of the brain, right? So that's why I see a symbiotic relationship between ontology and deep learning. And in the future, this notion of neurosymbolic AI is going to be a huge area of research. Okay, well, that was quick, but I'll stop here.
Thank you, thank you. It's a fantastic presentation.
Oh, my pleasure. Let me actually see if I can. All right. I stopped sharing, I guess. Did I?
We are still seeing your slide, but it's fine. You can keep it there. I'm wondering if there is anybody in a group who has a question. Okay, Thomas. Oh, Thomas is clapping.
Can you give me a second?
Yeah, I'm just applauding, but I think Mitra has her hand up.
Oh, okay. I didn't see it.
Thomas.
Okay. Yeah, he let's wait for him to come back. Okay.
Okay. Thank you very much. Your presentation was very interesting. I have several questions for you. So at the beginning, maybe slide 4, 5, or 6. My question is, do you use agent-based modeling?
Not for all use cases. Yeah, at some point we use agent-based modeling for building supply chains such that software agents can work together to create a supply chain. But it has not been a recent work. Maybe like I had a project like 4 or 5 years ago, yeah, that use agent-based modeling.
Okay, great. And then what ISO standard are you using for natural language definition?
Well, we use 704, ISO 704. I can Yeah, this is the standard that we use. I mean, it's not necessarily the best one, but there aren't that many standards out there, and that fits our need, kind of. But I'm sure there might be more better, useful standards.
Great, thank you. And then you said there are some problem with deserialization using Protégé. Have you looked at Toprate Composer?
I've heard of it, but I've not used it.
Okay.
Have you? Do you have experience with that?
Yeah, I have it on my FDA laptop.
Oh, okay. Yeah, Toprate Composer, right? Okay, I'll take a note of that.
Yes.
Yeah, because
no problem. The last question: what is the name of the open source tool that you developed that converts CSV file to knowledge graph?
Well, we don't have a name for that because
you don't have a name. Okay.
My student developed that. I can. Yeah, I mean, the problem with that is it's for specific data structure. It doesn't work for all CSV files, but that's something that we are working on. So that kind of make it more generic purpose tool. Yeah.
Good. Thank you.
Oh, sure.
Thomas.
Yeah. Thank you so much. For some reason, I'm not showing on over the background, but that's fine. So this is very interesting, and I was wondering when you talk about semantic interoperability, that it sort of implies semantic content that you don't necessarily always have or need when you have things like a supply chain record, or right, there are instances where you may need semantic content like medical records, or when you have a free text sort of narrative maybe, but very often you don't, right? So can you give us sort of a kind of like your view on how often, what are the use cases where you actually really need to leverage semantic content, and how does that affect sort of where you are on that? When you had that first chart, was, by the way, it was excellent, where you had the chart with interoperability and the complexity of the ontologies going from list to taxonomy. So where are your use cases on this chart? Like, how often do you actually need semantic interoperability and real ontology, as opposed to having a controlled vocabulary that sort of unifies the terms, and that's maybe enough?
Yeah, that's a great question. Well, we don't need semantics all the time. Suppose that we are a company, and within our company we have a good understanding of like what inventory means, or what a supplier means, or what a customer means. So yeah, then if that understanding exists internally, there is no need to define semantics explicitly, because when we say customer, we all know what customer means, right? Or when we say inventory, we all know. But the problem becomes more critical when we have multiple parties working together, and they have their own contextual knowledge and background. And for them, maybe customer for me has a different meaning than customer for the other company. So in those situations, we have multiple agents working together, either human agent or software agents. So that then the problem of interoperability becomes an issue. So so we need to come to a consensus, and define the meaning such that it makes sense for all the stakeholders. And that's a challenging part, right? So it's difficult to make sure that we all have the same understanding of the terms. And yeah, so but if that interoperability problem is supposed to be solved, we need to go over that difficult stage and try to get to consensus. Yeah, so my short answer is when there are multiple agents involved and there is information exchange between these agents.
I see. So can you maybe define, there's two ways to going about this, right? One is the ontology on top of your whatever learning model you have, right? You have the ontology on top of it, or you may just have a limited language model. When there's finite language, there's finite language models, right? Or there's finite, no, not language models, but there's finite domains. When you're analyzing legal text, for example, or you're analyzing, so you have, even without without defining an ontology, you have a finite finite language model. Is that replaceable? Like do you wonder what is the instance where you really need the structure and the expressivity of ontology as opposed to just limiting the language model to what the domain requires? Am I making sense?
Yeah, of course. Yeah. So, well, here automation becomes a factor. So, like a thesaurus, for example, here it's like a dictionary. It is a language model. It has the definition of all the terms, but it's not understandable for computers, right? So, I mean, large language models, they don't understand the meaning. They just work based on a statistical model. So without that formality, without adding those axioms, then we don't have automation, right? So we cannot send information to a computer and hope the computer understands what those things are. So yeah, and if we can add semantics, then we can do a lot of reasonings, right? So automated classification. So those things, those reasoning services that are very, very, very critical. It's like in machine learning, we develop like an algorithm. We train the algorithm. So reasoning is counterpart of training. If you remove the semantic models and axioms, then we cannot do reasoning, and it reduces the utility of the ontology. I mean, it still, ontology is providing us a unifying framework in terms of terminology, but it stops there. It doesn't go into reasoning.
Right. Okay, that's excellent. Thank you so much. This is super interesting. I don't want to hijack this. I see.
Oh no, that's fine. My pleasure.
Yeah. I don't know if you have time. But one question for Farhad. I mean, in the pharmaceutical industry, is kind of an ontology-free zone for the most part. What's the success you've had in other industries? Bringing ontology in. In aircraft manufacturing, perhaps that has worked. I mean, in the oil or chemical processing industry, to get the whole industry to adopt a common ontology. How do you, I mean, in the GSRS, we're trying now to deal with manufacturing. I mean, the FDA, somebody has to deal with the supply chain in the pharmaceutical industry because there's just all kinds of shortages. To go to ontology would be probably difficult at this time. But how do you get that to actually happen, I guess, Farhad? And has it been successful in, getting a lot of companies together to really say, we're going to do this and use an ontology? Asai is, helping us in a couple areas right now to try to bring an ontology in what we call the IDMP and perhaps in vitro pharmacology. But how do we go about doing that? And do you have any real success stories that, you can,
in fact, I'm familiar with IDMP. Elisa, I forgot her last name. She's in charge of developing it. Yeah, but well, I mean, one area that ontologists have been successful is biomedical industry. That OBO Foundry, it started with gene ontology, and it has been used very widely. So my understanding is that in biological and biomedical area, it has been used widely, and in fact, BFO is used there as well. In oil and gas industry, yeah, it's used very widely. Again, the problem is that in the US, we are kind of early. I mean, we are not that far in that respect. That's why we are we build this IOF to enhance and accelerate this process. Right now, we have received so DoD is very much interested and they are using it. So their ontologies are not open ontologies, but they have realized the advantage and importance of ontology, and they drive a lot of other industries. So we are hoping that we start with big players like aerospace industry and automotive industry and show success stories, and then go to the other fields. But right now, the situation, the climate is much better compared to like 5 years ago. People are more receptive and open to test ontologies. So I'm optimistic. Yeah, I used to be not very much optimistic, but now I am.
Yeah, so can we go over for 2 or 3 minutes? Do you still have a next call?
No, I have another. I can stay for 10 more minutes easily.
Oh,
yeah.
great. So I have 2 questions. One is that you have the supply chain modeling, and you also put data there. And I saw from all these knowledge graph vendors, one of their big use case is supply chain. So have you ever compared your approach and their approach? I mean, their approach may not be an ontology mapped ones, right? They can just create very simple knowledge database, graph database, as you said.
Sorry, I missed the first part. Who else is working on that? You mentioned.
Oh, I'm just saying that if you look at all the knowledge graph vendors, one of the big use case is supply chain.
Yeah, I mean, supply chain has different aspects. It's like a huge problem. So traceability is just one aspect of it, right? So, but yeah, there are multiple dimensions to that problem, and I'm sure people have addressed it in different ways. Yeah, so and maybe it's not based on ontology, which is very much fine. They use blockchain a lot. But again, I mean, it doesn't mean that we need to use ontologies for all scenarios and situations. Right. Use it when we have data issue, right? When the quality of data is poor, data is fragmented, and there are lots of gaps. So in those situations, yes, ontologies can be used for data alignment, gap filling through reasoning, and expanding the knowledge graph. So if you work with messy and heterogeneous data, yes, then definitely there is a motivation for using ontologies. But sometimes you are simulating the process and everything, data is very clean and in perfect situation, and everybody understands what's going on within that simulation package. So then, yeah, there is no need to use ontologies, right? So it depends.
Okay, and then another question is that you had shown a simulation data example for 600, and then you generated a big triples like 290K, and then you said even your own ontologists feel that sometimes it's hard to construct those Sparkle queries. So do you think that you need to simplify your engineering part of the ontology so that when you have a triples, the people who are conducting the Sparkle query can do an easier job?
Yeah, it becomes challenging when you have multiple ontologies imported together. So then if you want to run a query, you need to understand, okay, what is, for example, a custody change, or what's a business organization. So having a good understanding of all these different classes and properties, it takes time. But the thing is that the end user doesn't need to worry about these complex queries. We don't expect domain experts in agriculture run queries. That's why we went towards visualization. And there are ways for creating user interfaces that instead of typing this complex query, you can just select, okay, yeah, from drop-down menu, you build your query and run it instead of using a SparkQL. You don't need to see this content, the syntax at all. So yeah, then there are two ways. It's all about user interfaces. User interface for creating queries and visualization. With these two together, of course, you'll have queries in the background. And yes, so it's complex, but yeah, the software engineers need to basically embed those queries. But yeah, the complexity comes from diversity of classes and properties. And for example, here BFO it's a class, but 00056. Then you need to go back to the ontology and see what these refer to, what type of entity it is. So yeah, but that's the complexity.
Okay. And then the last question is about a tool that you are mapping a CSV file into RDF. Is that more like, you said that the mapping part is in the backend, right? Mapping of the ontology and those fields. So is that, what do I want to say? What I wanted to say is this mapping process can be configurable or is already specified, because if it's configurable, I can upload all kinds of ontology that I developed, and then I create this interface.
Yeah, exactly. That's what we realized that we need to do. So, and in the next release, we'll make it more configurable. Right now, there is like kind of hard-coded link between these columns and kind of the properties that we care about. But yeah, there should be some flexibility in defining, okay, what are the properties I care about and how I want to build my triples. Hopefully next release we'll have that. Yes, but that's a very valid point.
Yeah, and this is a desktop kind of tool.
Yeah, this is a Java tool, executable file. Yeah, I mean, I can send it to you, you can test it. But yeah, so it's just an executable tool. And well, when grad students develop tools, there are some bugs, obviously, but it works fine for our purpose.
Thank you. Thank you.
Sure.
Great. I don't have any more questions.
Okay, my pleasure. Yeah, so I'll send you these slides. I can share with the group, but it was a great pleasure. And thanks a lot for the opportunity. I truly enjoyed the questions.
Yeah, thank you so much for talking to us. It's really great. Yeah.
Thank you.
Thank you. Thank you.
All right.
Bye.
Have a good rest of the day. Bye.
Bye.